question. Work out these exit questions. So the first one was to try to draw the molecular diagram of this guy, a triene, and to show the reaction with heat, the electrocyclic. So let's draw this up over here. Not all the gold trans. Something like this. That looks pretty good. Yeah. Okay. So energy along here. I'll have 6. One, two, I'll have 6 p orbitals, p atomic orbitals. So I need to make a 6 by 6 matrix. 1, 2, 3, 4, 5, 6, and then 6 up. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. So this would be the p atomic orbital on carbon 2. Then we have carbon 3, carbon 4. 2, 3, 4. Yeah. Carbon 6, carbon 7. And that's 6 p orbitals. Ended at 7 because we started on carbon 2. All right, now let me fill them in. Okay, so 1, 2, 3, 4, 5, 6 molecular orbitals. 1, 2. There we go. I need to start shading these in. I'm going to start off just shade the left side all on the bottom. That side's done. Next side, it's going to be symmetric across the bottom, so I'll shade the bottom, top, bottom, top, bottom, top, bottom, top, bottom, top, bottom, top. All right. And then the lowest one is going to be all in phase. How many nodes? 0 nodes. This one's going to have 1. And it has to be, the symmetry has to be center symmetric here. Center anti-symmetric. And there's a node. Next one, center symmetric. And there's another way you could do this, I believe. Let me see. That one works, right? Center symmetric, same, same, same. Node, node. So 2 nodes. But I think I could do that another way. Let's see. That would give me 2 nodes, but I'm not center symmetric here. I don't think I have 2 ways to do this one. Try again. There we go. So that is another way it can be done to have center symmetry, 2 nodes. But this is the correct one that we find through experimentation. On an exam, if you put this, I wouldn't probably mark anything off. Yeah, I wouldn't mark anything off. But this is how you do it. And the way you can see it, remember it, is the nodes kind of like build up this way, you'll see. So let's move on to the next one. I've got 3 nodes, center anti-symmetric. So those are anti-symmetric. Let's go anti-symmetric, or let's go up there. Up, down, down. Is that right? Yeah, I think that's it. Opposite, opposite, opposite. 1, 2, 3 nodes. And the nodes are kind of growing out. All right, next one, we need 4 nodes and center symmetry. Same. Let's go up like this. We got 1 node, 2 node. Why don't we keep these the same? And a node down the middle. Like it. Okay, and then finally the last one's easy. 5 nodes, center, anti-symmetric. Just alternate, up, down, up, down. 1, 2, 3, 4, 5. All right, there we go. And I'm like 95% sure this is correct. I can look online to double check.
Okay, here's my answer. Yeah, I did it wrong. I said I thought I was 95% correct, but no, I was close. But molecular orbital 5 is wrong. See how I have a node drawn in there? That doesn't make any sense. And yeah, the orbitals are shaded wrong. Even though they're center symmetric, they don't have 3 nodes. Or actually, you're supposed to have 4 nodes, yeah. So here's a correct answer. Everything's the same, but you'll see 5 is different. So we've got 1 node, 2 nodes, 3 nodes, 4 nodes. That's the correct way. And you'll notice they used what I found online. They they use opposite shading than me, like the bottom layer. They did the dark on top. That doesn't matter. You can start it however you want. And then they made their p atomic orbitals different sizes. See how this is smaller and that's large, a little bit bigger, a little bit bigger. So what that's about is like for example, this is carbon, in this case, this carbon 1's p orbital. So it can't use 100% of carbon 1's p orbital in the lower level because then there'll be none left for the other levels. So it's making it smaller to show, oh, I'm only using like 23% of carbon 1's p orbital for the first molecular orbital. And then I'm using more of carbon 1's p orbital for the second, so different sizes. And that's derived through the quantum mechanical calculations, which we won't go into, but it's interesting to see.
And we're getting good guesses at this. There's limitations to it. So now we're going to fill in 2, 4, 6 pi electrons. 2, 4, 6. That is our highest occupied molecular orbital and our lowest unoccupied molecular orbital. And this one's going to be done with light. So what will happen is we will shine light at this and excite the molecular orbitals in the following way. So now this is molecular orbital 3, molecular orbital 4. Now 4 has an electron, it's not unoccupied. Now it's a singly occupied molecular orbital, SOMO. And we're going to use this to determine our stereochem. Enough of them. Or this one. Alright, let's do it. I'm going to take the alkene, I'm going to twist it first this way. Twist it that way, I can see. Twist it that way this time. Here we go. Oh, that's not what I wanted. I've already got it twisted the way I want it. I was twisting this one like that one. There we go. And now I need to just take this, it's flat in the plane of the board, and go whoop that way, so it's coming at you. And I know this looks a little strange to have wedged on wedged, but imagine you've got this shape of the molecule, and it went like this. So I've got carbons 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 2, 3, 4, 5, 6, 7. And I'll add my methyl is pointing outward, it's trans, and my ethyl is pointing outward. 1, 8, 9. Okay. Now I'm going to add my p orbitals here. And those are the ones that are going to tell me whether these are cis or trans. And I have to use not the heat conditions, the highest occupied molecular orbital, but the SOMO molecular orbital 4, which has center symmetry. So these outer ones are going to be both shaded on the bottom. There we go. And if I decide to just go clockwise with this side, just doesn't matter whether I start clockwise or counterclockwise, but if I start clockwise, that's going to bring the light phase in, and my methyl will go up. A lot of times students have trouble with seeing that methyl pointing up, going up, but just make sure you can get that in your head. And then since I went light phase in, I need to go light phase in here, so this has to go that way. So this was clockwise on this side. This one had to be counterclockwise, just because of the way the faces of the p orbitals are. And when that goes that way, what do you think? The ethyl goes up or down? Up. There we go. So we're going to get the methyl and ethyl cis. And when this happens, this is called conrotatory. Not that that matters, as long as you know it's cis. So let's get the final product of this guy. Well, I'm going to show you one other thing. Let me show you this coming at us still. The methyl's going to point up, the ethyl's going to point up. It's going to be a hydrogen down. Look like that when you rotate, and this is going to be due to an overlap of the non-shaded p orbital and the other non-shaded, like that. Okay, let me draw it up again, just from the start, to show you the regio and then that stereochem finally. From 2, swing 7. Okay, and now I know the stereochem. I already did that first. That's going to be, these are going to be cis. So let me erase this guy. Say, add the stereochem. It'll be a wedge methyl. Almost dashed it. And a dashed ethyl. And it'll also produce the enantiomer. When we were looking at this diagram earlier where they went like this, the light phases came in. We could also go where the dark phases come in. That gives you the answer. So we get a racemic mixture of those two. Okay, then we're gonna do one of these backwards now. So how could I make this? What's that coming from? I can actually do the mechanism backwards, and it's actually a reaction. It can go backwards. So you go like this to there, and my methyls, they can be actually that way, or both in, or one trans, one cis. All of those will work, and it just depends on whether you'll need light or heat for them. So what I do at this point is I just try. So for example, let's see if I use this one here, and I use heat first. So I know that if I imagine this coming at me, that's going back. This has got 2 pi electrons, so it's going to be, the molecular orbital diagram is going to be filled in. It's got 4 pi electrons, two alkenes. It's going to have 2 electrons and another 2, so it's going to be in the second molecular orbital, which is not center symmetric but center antisymmetric. So center antisymmetric. And if I rotate this guy clockwise so the light phase goes in, that will make the methyl point upward. And if I do that, then I have to rotate this one also clockwise, con-rotatory, same direction. And that makes the methyl point downward. So, will this be the correct product? No, this will give me trans. But what am I asking for? Cis. So I know the answer now. It's not heat, it's light. I know that because when I use light, it's going to excite an electron up one level, and that's going to cause the phases of the p orbitals to be in phase, and so then I'm going to get different rotate. It's all going to work out. All right, so it's going to be light, and that's my answer for that one. And I don't want to draw the dash methyl for this one because it'll be the exact same molecule just flipped over. So that's my only meso compound. Now, what about for the one that's this way? Do you think that'll be any different? I want you to check it, but you'll see that that should be exactly the same. You need light again, and it'll give you that again. Then, when I go to one that has one trans, well, not trans, one E alkene up here, and one highest priority here, one Z alkene down here, then I'm going to need to do that one with heat. I want you to confirm this. Check it. Go through the process. So in these reactions, there's 3 variables. There's the number of pi bonds. This one has 2 pi bonds, 2 alkenes. So you have that variable. Then there's the heat or light, because the light promotes you up to different symmetry orbitals. And then there's the cis or trans, or it could be E, Z, stereochem at the ends that determine. So you can look up rules, but I think it's better to derive it. When you just memorize a rule, you tend to when you apply it, don't really understand it and make a mistake. you want to use the rules, I would do this and then say, did my rule confirm it? Use it as a confirmation. Okay. Now we got a retro here. So for this one, I'll drop this first stereoisomer. And I'll say plus all the other stereoisomers. And when you look at this, hopefully you'll think to yourself, oh yeah, this looks like an epoxide addition. Because looks like we need to make a bond there, 1 carbon away from the alcohol. So let's do that. There we go. And plus other stereoisomers. For the retro, I'll just do that for this one. And then this can come from an alkene, which can come from a diene such as that one. And it may take either heat or light. I'll figure it out in the synthesis. And then the alkyne can come, of course, from the dibromide, the alkene, bromide, the alkane. All right, so we have our retro. Let's do our synthesis. I'll make the alkyne anion. I'll make the epoxide first. What did I start with? Oh yeah, this. I'll just try heat first and I'll check it. So heat, it's going to be center symmetric, center anti-symmetric. When I do that, the methyl goes up on this side, and it goes down on that side. Oh no, it goes up on that side. Long day. All right, there we go. So up. Wait a minute. I'm gonna go light in. I gotta go this way. That's right. It does go down. There we go. So light to light will make trans, huh? But I want cis, so it's gonna be heat. Then I'll add my MCPBA. And I'll get the wedged. That's good. The wedged epoxide plus the diastereomer, the dash. Okay, and then I'll make up my alkyne anion. So I'll start with my alkane. Let's go bromination, light 2, we'll go T-butoxide, potassium, T-butanol. Got our alkene, ER2, methylene chloride, or carbon. You can do methylene chloride. Then I'm going to go 1A, sodium amide, liquid ammonia. And then for part B, instead of adding water, we'll have the anion at that point. Let's add the epoxide. So oxides, and then that's the target molecule, huh? Yeah. Target molecules, lots of the 4 stereoisomer. Oh no, I need one other thing, huh? After the anion adds, it's going to have an alkoxide, so C, I need to add an acid more. Okay, time to go home.
All right, so okay, we got an ether combustion reaction we're going to do. Demonstration. Diethyl ether is very flammable. It's one of our most flammable solvents. It can react with oxygen in the air to make carbon dioxide and water, but is that equation balanced? Let's look at the formulas. 4 carbons over here, 10 hydrogens, and 1 and 2, 3 oxygens. Over on this side, we got 1 carbon. Nope, carbon's not balanced. 2 hydrogens and 3 oxygens. So the carbon's not balanced. Let's balance the hydrogens first. One strategy is leave the if there's any molecules with only a single type of atom in it, balance those last. So I'm going to go hydrogens first. So I'll put 5 there. So now on this side I've got 10 hydrogens. Oh, I just balanced the hydrogens. Now let's balance the carbons. I've got 4 because I got 4 there. So now this side I've got the carbons balanced, the hydrogens, but the oxygens are off. So if I come over here now to do the oxygens last, if I go 6, that makes 12, 13. Look at that. Now we're all balanced up. So we're going to have 1 ether reacts with 6 oxygen molecules to make 6 carbon dioxide molecules, 5 water molecules. Here we go. Ether fumes are actually heavier than air, which makes them pretty dangerous. So here's our air, mostly nitrogen, some water, some oxygen, and some... I didn't put any carbon dioxide in there, but that's in there as well. And then the ether, if it's in air, it actually sinks down. It's heavier than air, and that makes it dangerous because then it can go and get underneath things, ignition sources like under a fridge with a defroster or under a hot plate. Okay, let's see it.
Much more ether. Let's see.
Ether fumes are tumbling down. Nope, they got it. Pretty cool, huh? Now this has got a little bit more fire going there. Smother it. Might take a little more effort. More fuel. So it's getting a little bit of oxygen in the side of the beaker, so it's still going, but I can try to move the sand over to block it off.
If you have a small organic fire, beaker's a good way to try to put it.